Section 3.3a, Properties of Logarithms. In your calculator, whenever you use the common log key, the log, one abbreviated log, not natural log, but common log, anytime you push that button on your calculator, it is understood that you are working in base 10. So how do we handle situations in our calculator where we don't have base 10 in our logarithm? Well, we do that using the change of base formula. Change of base formula simply says that we can take the log of the argument, divide by the log of the base, or we can take the natural log of the argument and divide by natural log of the base. It doesn't matter. Either way, you're going to come out with the same answer. Next properties, if you remember your rules of exponents, and you remember that a logarithm is an exponent, then these next properties should follow from what you already know in working with exponentials. When we multiply like bases, x cubed times x to the fourth, how do we handle exponents in that situation? We add them, we get x to the seventh. Likewise, if I have a multiplication here in the argument of a logarithm, I can separate it into single logarithms by simply adding the two together. Same property as we have when we multiply like bases, we add exponents. Likewise, if we divide like bases, something like x to the eighth over x to the third, x to the eighth divided by x to the third, we subtract exponents and get x to the fifth. We're dividing here in the argument. If I want to separate that into separate logarithms, we subtract the two logarithms. Log base b of x minus log base b of y. Our fourth property is like when we have an exponent raised to an exponent. If I have x cubed raised to the fourth power, x cubed raised to the fourth power is x to the 12th because we multiply. I can take this y right here, pull it out front, and multiply it by the logarithm, and that's our final property. So again, remember that logarithms are exponents. The same rules that we have for handling exponents are the same properties that carry over into us working with logarithms. So up here, let's say that I have log base 3 of 20, and we want to evaluate that in the calculator. All we are going to do is take the logarithm of the argument, divide by the logarithm of the base, or you can take the natural log of the argument, divide by the natural log of the base. Either way, you're going to get the same answer. I don't care which one you use. If you want to use natural logs, use natural logs. If you want to use common logs, use common logs. It doesn't matter. You're going to get the same answer regardless. So letter A here. I'm going to take logarithm of the argument over logarithm of the base. Go to the calculator. Plug this in. Log 30. Make sure you use parentheses property. Close that argument. Divided by log of 4. We get that. Notice if we do natural log of 30 divided by natural log of 4, we get the same answer either way. So again, it does not matter. You don't need to necessarily write both of them down unless it tells you specifically to do that in the directions, but on a quiz or a test, one or the other is sufficient. So here we get 2.453. Again, keep in mind what that is that we just found. Always understand what it is you are doing when you are working with logarithms. Remember, logarithm is an exponent. So since we hit the log key, anytime we hit the log key on the calculator, remember you're finding an exponent. So in this case, we just found the exponent that goes on 4 to equal 30. In other words, 4 raised to the 2.453 power equals 30. Letter B is asking us the question, what exponent can we put on 2 to equal 14? Or 2 to what power equals 14? The way we can do that in the calculator, log of 14 over log of 2. Punch that into your calculator, and you should get 3.807, which means 2 raised to the 3.807 power is equal to 14. Expand each expression as much as possible using the property of logarithms. Okay, you're going to be expanding and simplifying using the properties that we talked about on the first slide. So in this case, if I look at the argument in this logarithm, we have a bunch of multiplication. If I want to expand this out into separate logarithms, and I have a multiplication in the argument, we know we can separate that out by adding each of the individual logarithms. So that's log of 5 plus log of x cubed plus log y. Continue expanding as much as possible. Our middle logarithm here, log of x cubed. What can we do with this exponent on the argument? We can pull that out front. So we end up with log of 5 plus 3 log x plus log y. Letter B, natural log of the square root of 3x minus 5 over y squared. Well, start in the argument here. I have a division in the argument. When we divide like bases, what do? We subtract the exponents. So when I divide in a logarithm, since a logarithm is an exponent, I'm going to subtract the individual logarithms. Natural log of 3x square root of 3x minus 5 minus the natural log of y squared. Simplify. Remember, a square root we can write as an exponent. It's an exponent of 1/2. Minus the natural log of y squared. And now, last step is we can take each one of these exponents and pull them out front of each of the logarithms. So we have 1/2 natural log 3x minus 5 minus 2 natural log y, and that's expanded out as far as we can go. Letter C. In this logarithm now we have both multiplication and division. We know when we multiply like bases, we add exponents. When we divide like bases, we subtract exponents. So we're going to have both addition and subtraction here. I'm going to have the natural log of x plus the natural log of y to the 4th minus the natural log of 2. Continue simplifying. I can take the exponent on this argument of 4, pull it out front. We end up with natural log x plus 4 natural log y minus natural log 2. The last one here, D, all multiplication in our argument. So when I separate it into individual logarithms, they're all going to become addition. So I have log base 4 of 2 plus log base 4 of x cubed plus log base 4 of y to the 4th. Continue simplifying. Log base 4 of 2. You should be able to do that in your head. Remember, that is asking you what exponent can we put on 4 to equal 2? 4 raised to the 1/2 power equals 2. So log base 4 of 2 is just equal to 1/2. That's the exponent. Plus, pull the exponent from the argument out front. In both of these two cases, and there's nothing more we can do to expand or simplify. So there's our expansion of that expression. Last one here. Use the properties to verify that this equation is true. If you get a problem like this, you can only work on one side of the equation, and you need to use the properties on that side to show that it can be simplified to what's on the other side. So I'm going to use, since we're expanding things out, I'm going to take this compact expression here on the left, and I'm going to begin expanding it. We have a division in the argument. Division in the argument of a logarithm. We can subtract the individual logarithms. Begin simplifying. Log base 4 of 1. What's that equal to? Well, what exponent can I put on 4 to equal 1? That's just going to be 0. Which leaves me with that. Now from here, the only way that I can simplify this logarithm more without going directly to the calculator and using our change of base formula is if we can somehow write 48 as powers of 4, because that's the base that we are working in. Well, 48 I know is 16 times 3. If 48 is 16 times 3, now in the argument here I have a multiplication. So let's separate that by adding the individual logarithms. Keep simplifying. Log base 4 of 16. What exponent can we put on 4 to equal 16? That logarithm is just equal to 2. Distribute the negative through, we get negative 2 minus log base 4 of 3, which is what we needed to show it was equal to.